Hi everyone. Today I want to tell you about how we can understand the Fourier series of periodic functions by connecting that to the concept of eigenvalues and eigenvectors of a symmetric linear operator. I need to tell you a little bit about symmetric operators. I want to remind you about how they work just in Rn in finite dimensions, and then kind of build towards the goal of talking about Fourier series and how it relates to eigenvectors, basically. So let me remind you first. So a linear map T from Rn to Rn is just a function that satisfies certain special properties. So first, it preserves the addition of vectors. So if you take t of a sum of two vectors, that's equal to t of the first vector plus t of the second. And if you take t of a number times a vector, this number, the number just slides out of the map, right? So it preserves scalar multiplication. So this is the linear map from Rn to Rn, and we know that every linear map has an associated matrix. Has an associated matrix. In this case, it's going to be an n by n matrix, such that if you apply t to a vector v, that's just multiplying the vector v by a matrix. Right? And we say that this map is symmetric. We say that T is symmetric if the matrix associated to T is symmetric. And that means that A transpose is equal to A. Right? So that's what it means for a map to be symmetric. And this is an okay definition of what it means for a map to be symmetric. But the problem for us is that we want to talk about linear maps in function spaces. And for those maps, we don't really have access to a matrix associated to that map, right? This only works in this case. Well, to a certain extent, it only works in the case where the vector spaces are in. So one of our first goals is going to be to say, what does it mean for a linear map to be symmetric without referring to the matrix A? Okay. But first, let me discuss a few examples just to refresh your memory. So just a few examples of linear maps, and let's talk about whether they are symmetric or not. Okay, so one, you could consider the map, say, t of xy is equal to 2x comma negative x plus 3y. Yeah, so this is a linear map. You can show that. It's easy to compute the associated matrix. A in this case is equal to 2, negative 1, 0, 3. And this means that, of course, if you want to compute t of xy, this is the same as multiplying this matrix 2, negative 1, 0, 3 by the vector xy. So you can write t as multiplication by a matrix, Remember, we always denote vectors as vertical matrices, column matrices. That's important. And we can see that for this map, the matrix is not symmetric, and so this map is not a symmetric linear map, right? So you can see here, let me write it in a different color, A transpose, if you switch columns and rows, now the first column is 2, 0, and the second column is negative 1, 3, which is clearly a different matrix, right? So this is not a symmetric map. Okay, so for another example, 2, let's consider now in 3 dimensions t of x, y, z, 2x plus 3z, 4y, and 3x minus z. All right, so the matrix associated to this map is a 3 by 3 matrix, because this is now in 3 dimensions. It's the matrix 2, 0, 3, 0, 4, 0, and 3, 0, negative 1. Yeah, which means again that if you want to compute t of x, y, z, that is the same as multiplying this matrix 2, 0, 3, 0, 4, 0, 3, 0, negative 1 by the vector x, y, z. Yeah, that's what it means to be the matrix associated to the linear map. And now for this matrix, if you want to compute its transpose, A transpose, now the first column of this transpose matrix is the first row of A, which is 2, 0, 3. The second column is the second row of A, so 0, 4, 0. And the third column is the third row, so 3, 0, negative 1. And you see that it doesn't change, of course, right? It's a symmetric matrix. You can see it's symmetric because if you reflect basically your matrix along this diagonal, right, so if you reflect the numbers, it doesn't change the matrix. Okay? So it's a symmetric matrix, which means that this is a symmetric linear map. That's a really good thing because basically, well, one very good theorem we have is the spectral theorem that says that a linear map that's symmetric only has real eigenvalues, and it's diagonalizable, right? So there's a basis of, in this case, R3, constituted of eigenvectors of this linear map. Okay, so those are some examples, but we need to talk about how to tell that this function t is symmetric without looking at its matrix, without referring to the matrix A, the associated matrix. And here the thing is to basically remember that, you know, if you have two vectors v, say v1 in Rn, so v1, v2, vn, and w, a vector w1, w2, wn, let me remind you that the dot product of these two vectors is just a number you get by multiplying their components together. So first component of V times first component of W, second component of V times second component of W, plus nth component of V with nth component of W. Right, so that's the dot product between them, which you can write as a matrix multiplication. You can write this expression as you take the row matrix V1, V2, Vn, and you multiply it by the column matrix W1, W2, Wn. Yeah, you can write it as a matrix multiplication. And so the way we're going to write this in shorthand is that, remember I said every vector should be written, if you write a vector as a matrix, you should write it as a column matrix, as a vertical matrix. And so this laying down vector here, this row matrix, this is not V, that is V transpose. Yeah, because if you take V, the column matrix, and you transpose it, you turn it into this row matrix, then you multiply it by W as just a vector, a vertical matrix. So this is a neat little identity that's going to let us understand symmetric operators a little bit better. Okay. Hopefully this makes sense. That on the left hand side, this is a dot product, yeah, of two vectors, while on the right hand side, this is a matrix multiplication of two matrices. V transpose is a laying down matrix, a row matrix. W is a column matrix. So now, let me get a new page. So using this identity, we can talk about a linear operator being symmetric without actually talking about its matrix. So suppose T so this is actually a general statement, not a statement about symmetric operators, but suppose that T is just any linear operator, or T is a given linear operator, yeah? And let A be its associated matrix. At the end, we're not going to have to refer to it, but at the beginning we do. So let A be its associated matrix. The idea is to look at the expression, take two vectors, V and W, and look at T of V dot W, a dot product. Okay, and we want to rewrite this. Basically, the question here is, if you have a dot product of T of V and W, is there any way to take this operator T that's on the left vector and send it to the right vector, right? So can you somehow pass this T over V? Okay? And the answer is you kind of can, in a way. So what you can do here is you can rewrite T of V, we know, is the matrix A times the vector V. Yeah. And that's dot product W. And from this identity here on top, you see in purple, the dot product of two vectors is the transpose of the first times the second. So in this current identity then, we can write this now as a matrix multiplication, matrix A times vector V transpose times W as a column column matrix. Okay? Now this is all matrix multiplication. There's no dot product anymore. Now the good thing of this is that we know in general, if you have two matrices A and B, then the transpose of A times B, that's the same as B transpose times A transpose. It flips like this, yeah? And so here, when we're writing AV transpose to kind of distribute the transpose, we need to flip. This is V transpose times A transpose times W. Yeah. So let's go over here. Now this is equal to, what I want to do is I want to take this V transpose, put a little parentheses here to make things a little bit more obvious for what we're going to do. This is V transpose times this vector A transpose W. And again, from this identity here in the purple box, V dot W is V transpose times W. Here we have V transpose times A transpose W. If you want to write this as a dot product, this is V dot A transpose W, which this is a different linear operator, is the linear operator whose associated matrix is the transpose of the matrix A, right? So let's just give that operator a name, I guess. It's V dot T star, say, of W. Okay? And here's what we find. So we can write it just in terms of T or just in terms of A. If you have a linear operator, TV dot W, you can send T to the other side, but then you need to star it, right? You get this other operator. Sometimes it's called the adjoint or the dual operator. Right, so for any two vectors, you get that identity. Or if you want to write it just in terms of matrices, we find that for any square matrix, AV dot W dot product is the same as V dot product A transpose W. Okay, so this is the identity that we just proved now, right? Here we write it in terms of the matrix A, there in terms of the linear map. Now, the good thing is that this identity lets us characterize what a symmetric linear operator is. But you can say the following. I'm going to write it as a proposition. So we said an operator is symmetric if its associated matrix is a symmetric matrix. Right? So A is equal to A transpose. Now, this proposition says a different way of saying that an operator is symmetric. A linear operator T from Rn to Rn is symmetric if and only if for any two vectors any choice of two vectors V and W in Rn, we have T V dot W is equal to V dot product T of W. Okay, so this is an equivalent way of describing, let me box this whole proposition, it's pretty important. An equivalent way of describing a symmetric operator. And now I don't need to talk about the matrix of this operator. Yeah, it's just a property that this operator satisfies, how it preserves the dot product in a way. So you can take T of VW, so T of V dot product to W, and you can send the T to the other side. Right? And if that's the case for any vector V and W, then your operator is symmetric. Okay, and so this is a good stopping point. In the next video, I'll show you how we can think of the second derivative of a function as a linear operator, but not in Rn, in this space of periodic functions, and show this property for the second derivative, showing that the second derivative then is a symmetric operator. All right, so I'll see you in the next video.